Good morning, everyone. Welcome to the NCT Data Science Seminar. This event is jointly hosted by Heidelberg AI. A warm welcome to Gitta, Kutyniok, our speaker today, and to Klaus Meyer-Hein, the chair of today's seminar. We would like to discuss your questions after the talk, but you can also use the chat function. Yeah, Klaus, I will hand over to you for a short introduction.
Thank you, Doreen. Good morning, everyone. I'm Klaus Meyer-Hein, today's chair of the seminar. So it's my great pleasure to introduce to you Professor Gitta Kutyniok. She holds a chair of mathematical foundations of AI at LMU in Munich. And her academic journey includes a doctorate from the University of Paderborn, a habilitation at the University of Gießen, and an international research experiences at prestigious institutions like Princeton, Stanford, and Yale. And before joining LMU, she held a professorship at the University of Osnabrück and at the Technical University of Berlin. And I'm very much looking forward to her talk today. Her research areas include applied harmonic analysis, machine learning, also sparse approximation, and applications in life sciences, but also in telecommunications. And today she will talk about reliable and sustainable AI in medical imaging and providing her insights into the opportunities and complexities of applying AI in this critical field. So join me in welcoming Professor Gitta Kutyniok. Great to have you here.
Yeah, thanks very much for the very kind introduction. Also, thanks a lot for the invitation. It's really a great pleasure, honor for me to give a talk here. So let me start by sharing my slides. Okay. Yeah, I think we all know how tremendously successful AI is these days, in particular in the medical field, medical imaging. But we also know that there are still, some problems, in particular concerning reliability and also sustainability. And with this, the energy efficiency. And so in my talk, I would like to take you on a journey to show you a bit the more also theoretical perspective on this, on different aspects of reliability, sustainability, always targeted mainly to medical imaging. But let me start by saying that I think we all know that we are at the beginning of the fourth industrial revolution through artificial intelligence. We see that society changes all around us. From production over telecommunication, also very sensitive areas like, for instance, the legal system is now already being infused by AI-based approaches. And then certainly all areas of sciences ranging from medicine, biology, over to humanity. So if you look into the future, I think during the next 5 to 10 years, you will see a radical change of our society in its full breadth. And so, in a situation like this, there are also some warning voices. And there was an interesting incident which happened actually now. You can read it. 6 years ago, there was a big AI conference and one researcher won an award. And in his plenary speech, he claimed that machine learning, and so AI, is still at the level of alchemy. So you can read, he said, researchers do not know why some algorithms work and others don't. Now we are, many years later, we've done a lot of research, but still, to a certain extent, if you train neural networks, it's a bit, a mystery why things work that well. So we have still a long way ahead of us. And also, if you consider, reliability, in particular also in the area of health, you see that there are still certain problems. Yeah? So for instance, concerning safety, there were already accidents involving robots. So this is related also to the problem of robustness of AI. Certainly also problems with security. So one can hack into those systems, changing things slightly so that the AI makes a radically wrong decision. There's always this privacy issue, since in particular in the health sector, having massive amounts of data is a tremendous problem. And so there are privacy violations happening worldwide. And last but not least, also problems with, I might call it responsibility. So many of these decisions are black box decisions. We still don't know how decisions are reached and decisions can be biased. So in that sense, I think it's fair to say that one current major problem worldwide is still lack of reliability of AI technology, as we need it in particular for areas which are critical. And in this respect, I mean, one can also look at international policies towards reliable AI. We all know, I mean, everything started with the Hiroshima AI process by the G7, who set very general guidelines. Then next came the executive order of the United States. And now in Europe, we have the AI Act of the European Union. You see a couple of requirements here. Maybe what might be known to many of you is this right to explanation. So every AI technology has to come with an approach to explain the decisions. And so, I mean, from my perspective, and this is also, if you look in the Aktionsplan in Germany of the Bundesregierung, AI made in Germany should be a guarantee for reliability. But I mean, from my perspective, this can only happen if you really know the technology in its depth. So what we require is a profound mathematical understanding. So in that sense, as said, I would like to take now a more mathematical, theoretical perspective. Don't worry, there are not too many formulas in this talk. I would like to just give you a bit, let's say, a feeling of what can be done, what has to be done, and where the journey is heading towards. There's another problem, which to my mind is a bit swept under the rug these days, but is maybe even more important, which is the energy problem. And so you might have seen, if you're on Twitter, news like this: Oracle will use 3 small nuclear reactors to power the new gigawatt AI data center. And so there are also studies of this type, where you see here the world energy production, and you see the energy which is just needed for specific areas here, for instance, for communication, heading straight towards the world energy production. So in that sense, I mean, this energy limit is a fundamental barrier for any type of AI in any sector, so also in the health sector, where you deal also with this massive amount of data. And so the sustainability is something I would also like to just briefly discuss then at the end of my talk. Okay, so let's now take a mathematical, a more theoretical perspective, just to bring everyone on the same level. Deep neural networks are the workhorse. Nothing new. It started in 1943 with McCulloch and Pitts to introduce artificial intelligence. And so the way they did that was they modeled the human brain. Yeah? So they developed a crude mathematical model of the human brain. And this, you might also all know, I mean, we have these artificial neurons. It's a mathematical formula where you have incoming signals, you have weights which amplify the signal. Everything is collected in the soma, and then deciding whether to fire or not depends on this bias, and how strong, let's say, the firing is depends on this activation function. So that's a mathematical model from one neuron. We connect everything to a neural network, and as said, I mean, this talk is not loaded with formulas, but I mean, this I would like to show. A neural network is nothing else than a function, which you see here, a concatenation of these affine linear terms and these activation functions. And so in that sense, it's accessible to all of mathematics, which we have, so we can analyze it in detail. Okay, so what are now the key questions we want to ask to understand more about how neural networks act and why they work that well? One area is called expressivity. So we have our network architecture, and the more extensive it is, the better it can approximate, let's say, the functions we want. So the question is how to set up a good network architecture to improve the performance the best way. Do we do it in a, let's say, a deep way or a wide way? And so yeah, so this is usually approximation theory from a mathematical perspective. It's the most developed theoretical area. Then learning. We all use stochastic gradient descent extensively. It's a bit still a mystery why it works that well. The problem is so-called non-convex. So you have several local minima. Still, this algorithm, for some reason, converges always to a very good local minima. And this is not clear why. So also a problem is this stochasticity in the process. And there are a lot of, let's say, researchers aiming to solve this problem and analyze in depth why this works that well. Then people call that sometimes the holy grail, generalization. What I would like to know certainly are success guarantees. I would like to know how everything performs on the test data set. And this is also a reason why, I mean, for critical infrastructure like telecommunication, for instance, in Germany, the Bundesnetzagentur does not use AI yet because these error bounds are not at a level which is comparable to what has been known for traditional methods. Yeah? So this is a key area. And so, I mean, there are a lot of people doing research in this direction. I mean, I would not like my talk to focus specifically on this because it's very technical. I would like to instead ask the question, I mean, in medical imaging, we have a lot of AI-based methods. So what can we do to ensure, let's say, a maximal amount of reliability? And so I'd like to show you some strategies which we pursue in my group, and also show you some applications in particular concerning computed tomography. In line with this is the area of explainability. So this aims to, if we now have a trained neural network, aims to understand how this network acts. This is another, let's say, assurance of reliability, and I just said this is also in the EU AI Act. So I would like to also discuss a bit that. I mean, what are maybe things we need to take care of, and what can one do? And last but not least, something from my viewpoint, which is also often not that much discussed, is every new key technology like AI has certain limitations. And so the question is, what are the limitations here of reliability? And what we'll see is there's a very exciting direction for the future. And this gives us also a bridge to sustainability in the sense of energy efficiency. And so in my talk, I would like to now discuss, I mean, these last 3 points in a bit more depth. So let's start with AI-based medical imaging. And here I would like to start with just very briefly reviewing one very classical method. And then we will see how we can integrate AI in a reliable manner in that. Now, if we do image processing, most of the time we solve an inverse problem. So we have, I don't know, our original data, we do something with it, I don't know, we take things out, we measure it, maybe with a CT scanner. So we have our measurements G, and from G and knowledge of K, we want to recover F. So almost all imaging problems are of that type. And there's a very classical method to solve those. This is also, I mean, what was said in the introduction, sparsity. So you see, you solve this optimization problem, and you have these two terms. So if you now aim to solve this and bring this to 0, you see you got, let's say, a perfect F which solved this inverse problem. But then, I mean, you might have a lot of Fs, and so therefore you have this regularization term to, from this large set of Fs, you pick the best one. So for instance, here in this example, if you haven't seen that, I mean, there are numerous ways to fill these gaps. And so the question is, what is the best filling? And so this regularization term in sparse regularization now uses the paradigm that you can always find a representation system which gives you a sparse expansion. And so this L1 norm promotes sparsity, and maybe you've seen pictures like this. So let's say this is my solution space just in 2D for explanatory purposes. If I would put here the L2 norm, I would minimize the L2 ball, and then this would be my solution here. But if I minimize the L1 norm, I minimize this diamond shaped, and this is the solution. And now you see this solution has 1 zero and 1 non-zero components, so it's much sparser. So L1 norm promotes sparsity, and so this is what is used in sparse regularization. Now, how do you choose this? This term here, I mean, there are numerous ways to do that. Wavelets is a very, very classical method. Many of you might know this. So the wavelet transform maps an image to these inner products, this image with so-called wavelets. You see a couple of wavelets here. And if you are more into mathematics, you see a definition of the wavelets here, represent a function which you translate and which you dilate. And so, I mean, the image of this transform you see here, and you see there are many black areas, which is where you have the value 0. That gives you the high compression rates. And so therefore, this is also the basis for the JPEG 2000 compression standard. Now, there's an extension of that, taking care of the fact that, I mean, directions are important. And So there, I mean, we introduced what we call shearlets. So these are systems which are more directional, adapted. Shearlets appear again at every position, at every scale, and also in every direction. So we have nice results that they fulfill certain optimality criteria, optimal compression rates for certain classes of functions. And I mean, you also have an extensive software library, shearlab.org, I mean, also with Python. And so one can play around that. I just talked about were traditional methods, which we have worked on for many years. Now let's come to one particular application, which is computed tomography. So computed tomography, most of you, I guess, maybe all of you know. So we have here let's say, for instance, the interior of the human body. We compute line integrals through it. This gives me a one-dimensional function. This is one slice of the sinogram, and then we'll rotate. And so we fill the sinogram one by one. And from the sinogram, you want to reconstruct the interior of the human body. This is not that difficult. It becomes hard if you have limited data. And so there are two main types of limited data. One is that to not expose the patient to too much radiation, you don't only require, let's say, for instance, each second angle or each third angle. That relates to the fact that here you have, let's say, only every second slice or every third slice. That is already difficult, but it becomes really hard if you go to limited angle computed tomography. Yeah, so limited angle computed tomography is for techniques where you cannot do the 180-degree sweep. This is, for instance, in electron tomography, where, I mean, as you see, if you turn this device, after some point, the rays cannot get through it anymore. Also for dental CT, you cannot do 180 degrees. That relates to the fact that now for the sinogram, you have a whole chunk of missing data. And certainly this is much more difficult than if you have only every second slice. And so computed tomography, I mean, this you can also all make this mathematically precise. It's the radon transform, which you sample. And again, you see here, let's say the function which you want to compute, which you want to measure. And you see here the different line integrals appearing at every angle and at every offset. Exactly what I said on the previous slide in words. You see here in formulas. And so the challenging inverse problem is if you can only sample this in a certain range inside this this interval from minus pi half to pi half. Okay, so how bad is it? So here, for instance, you have a 60-degree missing angle, and if this is your original image, this, I mean, very, very crude reconstruction, filtered back projection. I mean, the easiest you can do. It looks really bad, but also if you do more sophisticated methods like this bath regularization, which I just showed you with these shearlets, you see, I mean, it's not that great. Yeah, you see a lot of artifacts. I mean, a lot of noise. I mean, the problem is that it's too precise, too complex for precise mathematical model. Okay, so this brings now AI into the game, and we see, I mean, we cannot get further with traditional methods. So there's actually also no way out, and neural networks have to come into play and have to play an important role. Certainly, I mean, the easiest you can always do is the simple ad hoc method to train a neural network end to end. Yeah? So in that case, I mean, if you have this inverse problem, you would do the following. You have a lot of measurements, you have a lot of the original data, and then you train a neural network to just recover. This is easy. You don't need any physics and nothing for that, but it has also a lot of problems because, as said, I mean, these comprehensive theoretical guarantees are not there yet, because then you just have the neural network. You don't have these generalization bounds which you would require. So you don't have the reliability you need. It's also a black box to a certain extent. But more importantly, you have a lot of additional knowledge because you know, for instance, for CT, you know how the measurements are taken. So you waste physical knowledge, and also the neural network has to process the entire data, which is also from the energy viewpoint, maybe not the best you can do. So let me also say there are now, I mean, a lot of approaches which not use this ad hoc approach, but which combine this with traditional methods. And there are a lot of ways you can do that, in that sense, taking the best out of both worlds. So I might categorize them in 3 categories. One, I might call supervised approaches. So here, I mean, there are various ways. Maybe one of the most popular ways is this plug and play. So you have your algorithm, which we saw before. It's an iterative procedure, and at some stages it does denoising steps. And so you just replace this denoising step with a neural network. You could also incorporate the operator into the neural network if you do, let's say, this ad hoc approach. Then there are these semi-supervised approaches, which, for instance, here you replace the regularization term by a neural network. That means the neural network, I mean, doesn't need to, let's say, be trained on the entire data in the classical fashion, but only needs to indicate which of the images are better than the others. So therefore, more semi-supervised. And then there are these unsupervised approaches, where you use, for instance, deep image prior is very popular, where you just not train the neural network at all. You just parameterize the solutions as the output of a neural network. And so for all of those, I mean, the unit is for some reason the best. I mean, this is always the architecture which is chosen for inverse problems. So let me show you one method in a bit more detail. It's a very general overall strategy which we usually pursue, and I would like to show you also some examples to see that this, I mean, works usually very well. So we usually use model-based methods as far as they are reliable. Now, so we don't want to give up on them because we have these error bounds, and we just use them up to a point where they do not work anymore, and then insert the AI-based approaches in a surgical manner and then combine both worlds. So this has a lot of advantages, as you can imagine. I mean, you get, say, the reliability from the model-based approach, and you only learn what you cannot get otherwise. You have much better performance due to the better input for the neural network. And it's that edges are guiding features. So edges are very prominent structures in images. And in that sense, we put a lot of emphasis on this. And we typically use the shaded transform for that. What is this wavefront set? So here you see this image, you see the edges color-coded, and the color coding are the directions of the edges. So these are often important. You will see that on one of the next slides. And so this is basically this wavefront set. Yeah, so the points of the edges and their direction. And this is something which is extremely useful for a lot of reasons. Okay, so now let's go to the computed tomography problem, and I would like to show you 2 approaches. I mean, one is a bit an older approach which we developed, and then let's say the newer approach, but the older approach already shows, I think, very well this general philosophy. Okay, so what I show you here is if you just have a sweep of from -15 to 15 degrees and you recover by filtered back projection. It looks awful. And now you can increase the angle and it gets better and better. Not surprisingly. But what I would like to show you very early stage, even with this crude reconstruction, you can get very precise information about certain edges. And you get this information about certain edges depending on their directionality. Because if you scan in this direction, at a very early stage, you know that there must be an edge depending on its direction. So, I mean, certain singularities which are tangent to the sampled lines, they are easily reconstructible and visible. Others, I mean, just smeared out, there's no way. So you can make this mathematically precise, and you can phrase this also in very fancy terms using this, what I call wavefront set. So depending on their, so what you see here is you see here the edge points, and each edge point has a certain angle. And so this red line is what's called the wavefront set. Yeah, so the edges together with their direction. And so here, depending on their direction, certain parts are missing. And so in fancy terms, you can say this is a problem, an in-painting problem of the wavefront set. Okay, so how can you solve this? So we already talked a bit about shearlets, and so if you compute the shearlet transform, you can identify edges and their direction. Now, so this is a very nice feature, and due to the directionality, you can also basically see what are visible and invisible parts. So now, to follow this general strategy, we use, and I will show you the algorithm on the vast regularization with shearlets. We use deep neural network to recover, and then we combine both words. Okay, so this looks in this way. Step one. So we do sparse regularization. We discussed that. The operator is now the Radon transform. We have here the L1 norm. And this is my normal reconstruction. It is okay, but you have all these problems. Then we apply another shearlet transform. And now, I mean, some of the indices, this is reliable and nearly perfect. We don't touch them. And there are some in certain areas which are almost zero. And only those we modify. So here we have this F. We now bring it in the shearlet domain. And there we can basically now separate what has been reliably reconstructed and what not. And only those which are invisible, we now train a neural network to recover those from the visible part. And so then, I mean, we get this F, which now replaces basically what has not been recovered here. That means we now take these visible parts, we add the invisible ones, for which we use the neural network, and there was no other way we could recover them, and then we bring it back to image domain. Okay, so let's see how that looks. So this is data from a Mayo Clinic in the US. We have here a 60-degree missing angle. This is my original image. This is a crude reconstruction. The measures you see here is the relative error. And the harp psi is a measure like the self-similarity index, which is even a bit better, more adapted to human visual scores. Okay, so then this is TV reconstruction. It looks better. Then comes sparse regularization with shearlets, which is even more improved. Then this is an end-to-end neural network, which is better. It's more precise. But then if you, let's say, combine the best or take the best out of both worlds, I mean, you get a very nice clean reconstruction, although you have this huge missing wedge. And so if you like measures and metrics, so here we have relative error, PSNR, self-similarity index, harp psi. In all of those, this is the best. And this harp psi, let me say, I mean, this was something we introduced at some point. I think it's a nice measure because you can compute it much more efficiently than the self-similarity index, and it has higher correlation scores with human opinion scores. Now, this is nice. We applied this conceptual strategy also to other types of problems, for instance, to a very classical edge detector. So you would like to detect edges in that direction. Again, what we did was we used a classical method like shearlets, and then we used neural networks to improve on that. And so here it was used in a very specific way to, I mean, get more precise predictions of the direction. So again, I mean, first the classical methods as far as it goes, and then let's say a neural network. And so here you see an example, original image. This is a very good, both worlds, you get a very clear picture of the image, of the edges and their direction. So let's delve also a little bit deeper. And I would like to show you now, I mean, what we recently did. Again, it's a bit a similar philosophy. So there is a nice mathematical concept that you can, if you have your, so this was the wavefront set, remember the edges and the direction of the original image and the edges and the direction of the sinogram. And you can go back and forth between those. So that's a mathematical fact. Now, how can you use that? Let's assume you have your sinogram. What you can do is you can extract the wavefront set here, and you can bring it with the canonical relation to the data word. This you can view as, let's say, a model-based track, and you can use this then as a prior We combine this with an AI-based reconstruction, a bit more structured one, so one which is based on the primal dual algorithm, and then take the best out of both worlds. So I will show you, let's say, the flow chart in a moment. Let me just say, I mean, for the wavefront set extraction, we use this DENSI, which I showed you. The AI-based reconstruction is algorithm by Adler and Öktam, where basically the primal dual optimization method is unrolled. So it's a highly structured AI-based approaches. And so this enabled us to also do some theoretical analysis, but it was, I mean, extremely difficult. So we had to introduce ReLUs on distributions, a continuum learned primal dual. So I think the main message here is, because we have a lot of structure, we could perform some theoretical analysis, but it is still very difficult because the AI-based part is maybe missing that strong of a theoretical foundation at this point. But in any case, so this is the overall strategy. So here you have this classical AI-based reconstruction. You have here, in that sense, the track from model-based. So you extract the wavefront set, and then you bring it with this canonical relation to the image side, and then you use this as a prior for reconstruction. So here I just show a couple of images. You have now a 40-degree missing wedge. This is the learning the invisible, the previous what I showed you. This is if you just use the neural network, the structure we used end-to-end, and so then with this deep micro-local reconstruction, you can do even better. So I think the main message I would like to say is that so it is, from my perspective, not the best way to just use a neural network out of the box in that sense of training end-to-end, but I mean to use as much physical knowledge and as much model-based approach as possible. Okay, so let me also come now a little bit to explainability. So explainability, I'm sure you've seen these pictures. So you have, we have an image, the network says this is a 3, let's say, and then the explainability approach says, I mean, these are the areas the network looked at. And so you can find out, for instance, if the network did something very strange. So this is a nice example from my colleagues at TU Berlin. There the network only learned the copyright tag, but nothing about the structure of the horse. But now, I mean, you can ask, I mean, these relevance maps, I mean, they look nice, but you might want to know a bit more about what these red dots actually mean. Also, you might not want to have only pixel-based explanations, but more higher level explanations. And the ultimate vision in the field is to really communicate with the AI like you would with a human or with a doctor about a decision. With ChatGPT, we are a bit further, but still there's a long way to go. And also, I might caution that if we use explainability for ensuring reliability, then the explainability approach itself has to be reliable. Yeah, it's not sufficient to produce some nice pictures, but we have to trust it. And so from my perspective, therefore, also a mathematical foundation is important for that. And so let me show you one approach which we introduced, which is based on information theory. So here's again, I mean, an overview of various different methods. But let me come to what we introduced. So it's based on information theory. In a nutshell, what is information theory? And then we will phrase the explainability question in this way. Okay, information theory is one person has a message. She's always called Alice. She transmits parts of the message to Bob, and then he has to decode, and the message is distorted. So you have the rate, how much is sent, and you have the distortion, what the error is. And there's this rate distortion trade-off. So the more you send, the less the distortion. Okay, so now we phrase explainability in this framework. That's my neural network. And now Alice has the original image, and she has the neural network. And Bob also has the neural network. And so she has to transmit parts of the message to Bob. But she transmits now parts of the image to Bob. Hopefully the relevant pixels. Then Bob, to put it in his neural network, he has to obfuscate to bring it back to image size. And maybe he uses random pixels to not distort the meaning too much. He puts this in his neural network and he gets the distorted message. So you have how much you send, the rate, and you have the distortion, so the difference between the outcomes of the neural network. And so what you certainly aim for now, is a concise explanation. So you would like to have that the error is not that great, but that you optimize over how much you send. So that would give you a very concise explanation for the outcome of the neural network. If you work in this area, you know this is something you cannot compute. It's NPPP complete. I don't want to go too much into details there. You can relax this and get an optimization problem of this type. You can again see you optimize over the distortion. And now you optimize instead of over the number of pixels, you optimize over the L1 norm. And remember the sparse regularization, which we discussed before, L1 promotes sparsity. So you want still a concise explanation, but keeping the distortion under control. And so this allows also a rigorous mathematical performance analysis. I would like to show you just one result later. Okay, so here are a couple of images. So again, like a dog, the neural network says this is a dog. And so you see our explanations are tuned for sparsity. So you have very concise explanations. And here you see the network looked at the head of the dog to get this explanation, which is nice. So we extended this then in two ways. One of these random pixels look a bit strange, so you can also use an in-painting gun to fill it in a more natural manner. And maybe the more interesting aspect is you can use higher level explanations in a quite easy way. You can decompose now your image into, let's say, wavelets, for instance, and then put the relevance scores on the coefficients. And so this we call cartoon X. It's a bit in a similar fashion than compression. You have the input image, you have the wavelet coefficients. So that's image compression. You select the largest entries, you replace the others with 0, you reconstruct, and then you hope that you are close. This algorithm works in a similar fashion. You compute the wavelet coefficients, you select the largest entries. Now you replace the others with random noise. And then you reconstruct, and there's no way this is close, but to the lens of the neural network, this is close. So it's in this spirit. And let me just show you, because, let me just show you maybe this image, which is, a funny example. So here the network can, the explainability approach can explain decisions. And so here the network did something wrong. It said this is a diaper, and this is a screw. And I can overlay this now with the explanation, and you will see what the network has seen to reach that wrong conclusion. And so here, this looks a bit like a baby, and then a diaper is not far off, and this looks a bit like a screw. And so then, you can counteract and, let's say, modify the data and retrain to get rid of these artifacts. We also use then, these shieldeds, these directional systems. And let me just show you to conclude this part, that you can also do real mathematics with it and real theory. So what we found out is that if this is your original image, then the explanations sometimes have additional features which distort the explanation. So we looked at the edges, and the edges in the image and the edges in the explanations. Sometimes explanations introduced artificial edges, and so distorted the meaning. And so this we could in fact rigorously prove. I don't want to go into details there, but what we showed is that using the shieldeds, no new edges are introduced. So the edges and the direction of the explanation are a subset of the edges of the original image. So in that sense, you can do really hard mathematics with that. Okay, maybe in the last 2-3 minutes, let me also now come to an area which is very dear to my heart, about fundamental limitations and the bridge to sustainability. So what we looked at is people talk a lot about good algorithms, but the hardware is never that much considered. And so we asked the question, what can you actually compute on digital hardware? And you can model digital hardware as a Turing machine. So you break the typical continuous problems down to zeros and ones, and this has to cause certain problems. We approach that from a computability viewpoint. Computable problem is one for which the input-output relation can be computed on a digital machine for any given accuracy. If something is not computable, well, I mean, you can still run it on your machine, but, well, I mean, then you don't have guarantees for reliability. And so what we showed and what we found out, I mean, coming back again to inverse problems, is that the solution in general of an inverse problem is not Turing computable. I mean, we have very precise result. Again, I don't want to go too much into details there. What you can see is here, I mean, sparse regularization with the solution set. And then we showed there exists not a Turing computable function which approximates the solution set up to 1/4, which is far off machine precision. So that means that, I mean, there could be, some, let's say, some inconsistencies, some robustness problems in the background, which one might not observe at first glance. And so this is certainly a problem because we would like to have reliability for any of those problems to solve. But there's also a very interesting way out, because what we showed is if you go now to other hardware platforms, and so here we specifically went in the analog world, so the Bluetooth smelling machine, then things become computable. And so that might point to the way that reliability for certain problem setting might require novel hardware. And there are actually interesting directions which we see, and also companies like IBM and so on go in that direction. There's neuromorphic computing, which basically aim to model the human brain in a much closer way. There's biocomputing and quantum computing, I'm sure everybody has heard of. And neuromorphic computing has the advantage that it's also much more energy efficient than digital hardware. And so the hope is by next generation AI computing that we get reliability and sustainability. I mean, we just say we also founded the company now in this direction. So let me just spend maybe I think the time is almost up. 1 or 2 slides on this next generation AI computing. So the idea is to go from the classical von Neumann architecture, where we have binary input and output, now to this neuromorphic architecture again, which is closer to the human brain. And so the canonical neural networks for that are spiking neural networks. That's an analog version of normal neural networks. And so it's much more biologically realistic. And the key point here is that everything is not processed in a synchronized manner, but every neuron acts on its own. So for instance, this neuron here, it will get some inputs, spike inputs from different neurons at different times, and it builds up a potential, as you see here. And at some point, the potential reaches the threshold, and then the neuron fires. So information is encoded also in the timing. And so this also makes it more energy efficient, because we have another means to encode additional information. And so let me not go into the details, because the time is up. So you can make this all mathematically very precise. And so what we, for instance, showed is that spiking neural networks can be emulated by classical artificial neural networks in many cases. But typically, they are strictly better concerning efficiency, in fact, exponentially better. So emulated theoretically spiking neural networks by other neural networks, and then you needed an exponential number of neurons to do that. And so this points towards energy efficiency. And we just started also a large-scale project in that. I mean, it's set up between both states, free states in Germany, I mean, Bavaria and Saxony, to develop highly energy efficient AI hard and software, ensure reliability and compliance with legal requirements, and also apply to communication, medicine, and robotics. So this is what will keep me busy during the next years, I think. And let me now finish with some conclusions. To my mind, I mean, reliability, sustainability, these are still issues concerning AI, and it can only be approached from a theoretical mathematical perspective. We talked a bit more detailed about explainability and in general the area of medical imaging, and then also about the fundamental problem with digital hardware in that direction of analog hardware and the vision, which is, yeah, I think a vision in particular also for our large-scale project to get mathematically reliable and sustainable AI. And let me at this point also say that I think you also have one of these Konrad-Zuse schools. We have one of the Konrad-Zuse schools also in Munich between both universities. We focus on reliable AI, and you see here medicine, healthcare, and mathematical foundations are both, I mean, both pillars which we build on. And so with this, I'd like to conclude, and thank you very much for your attention.
Thank you very much for this fascinating talk. Very interesting stuff.